All right, can you hear me? Is the mic on? Yeah, I'm going to pull this off if that's okay with everybody. I'm pretty far away, yeah, okay. It's easier to lecture without the mask. I hope you had a nice spring break. Did you miss me? Probably not. All right, so let's see where we stand. Jeez. There we go. So I think I completed all pending regrades over the course of the break. I posted an announcement to Icon, and immediately somebody wrote and said, but you didn't look at this one. So if I didn't look at something you expected me to look at, send me a note. But please, let's use a subject line that says what this is for. I had to go through, I have like 15,000 emails in my inbox because I get a lot of stuff that I don't really care about. It just accumulates. If you don't put CS 1210, I'm likely not to see it. So please, just make sure you note it. I'd like to get these done today if I can. So we've completed grading of midterm 2, and when I say just completed, I mean at 2:55 this morning, the last TA wrote me and said I finished my set. I haven't had a chance to look at the grades yet. I'll do that today. And I don't believe the grades are posted yet, but they will be posted today. We're still working on grading homework 1. We're about a third of the way through, which involved developing a rubric, running tests, and the TAs who were grading the midterm, the ones who were last finishing the midterm, now have to turn their attention to grading the homework. So we're going to be a few more days for homework 1. But hopefully by end of day today, I'll have posted a curve on Icon so you can see where you stand, and I'll post a column in Icon's grade book that says, midterm grade or something. And that way you can see where you fit in the class based on all the work done so far. So I'll compute that later today, and either tonight or tomorrow morning it should be available. Okay, and that should let you see where you sit. Question day 11 posts today, and Lab 7, of course, is tomorrow. Are there any questions about what's going on, or is everybody sort of situated? The nice time at the beach or wherever you went, and now you're ready to get back to coding something every day? Yeah? Okay, so let's go over the midterm solutions. Since we haven't had a chance to do that yet. So there were 3 problems, and like I said, I haven't seen the graded versions of the midterms yet. I just know what the TAs have told me. Surprisingly, it appears that the hardest problem was the second one, the iteration problem. At least that's what I've been told. I can't really be sure about that because I haven't had a chance to look at the solutions or what you posted as solutions. So the first one is an in-order sequence. It asks you to take a sequence S, which consists of a set of words. And by the way, I'm paraphrasing here what was in the exam. I didn't copy exactly the same wording. And returns a list of Booleans where each true-false in the list corresponds to whether or not the characters in the corresponding word, when all taken to be lowercase, are in order. So just reading this should make you start thinking about other problems we've done, about how we go about doing this. But to make it clear, here's a sentence with 5 words in it, and D and O are, when you lowercase this, these are in alphabetical order. These are not. No, K-N-O-W is, and the other 2 are not. And same for Billie Jean is not my lover. Same thing, it's just is and not and my. These are the only words where the letters appear in alphabetical order. Okay? So that's what we're after. And by the way, you have to use a comprehension. So let's just build the solution step by step, like you would have done on the exam. So the first thing is, you know this much. You need to return a list, and you're told to use a comprehension, so let's use a list comprehension, which means my thing is going to look something like this. Now, there may actually be an if part to this comprehension, possibly. We don't know yet. But if you think about it just a little bit, if you just reflect on it, it's not likely to have an if part because we know that every word in that list is going to have a corresponding Boolean. We're not asking you to find only the ones where they're in order, although that could have been a problem. We're asking you to find which ones are in order and indicate a Boolean. So probably the if is not going to be there. All right? With me so far? Second step, I know I'm iterating over lowercase words in S. So let's just do that. I'm going to just iterate over words in s.split, gives me each individual word. And if I collect those words with the lower method, I'll get lowercase versions of those words. Simple enough. So now, instead of just collecting the word, I need to collect a Boolean that says true if the elements of this word are in alphabetical order. So at this point, I'm just down to focusing on the thing I'm collecting because all of the rest of the stuff looks right to me, right? It has the right behavior. It's iterating over every word in S. So I want to collect a Boolean that indicates whether W is ordered, and here is one way of doing it. You were given a pretty good hint. You were told to consider the sorted function, which is on your cheat sheet. And this does the trick. So we see that if I check that the lowercase word is the same as the sorted version of lowercase word, I'm in business. But in fact, I'm doing the lowercase stuff twice. So really, this is the solution I had for my word, was to turn the lowercase first and split it second. All right? So step by step, you just go through what the specifications say and use what we've done in class. So remember, build a list comprehension, do the test, and so on. Okay? Second one. So I think this one maybe was hard to understand. I don't know. I tried to give some examples, but the TA who finished this one, this is the last one that we graded, said that the class had a lot of trouble with this. So I asked you to return true from this function bitonic if L, which is a list or a tuple of integers, is bitonic, and I'll define that in a minute, and false otherwise. You can assume that the elements of L are unique positive integers. So that's important. It'll make things easier. You don't have to worry about corner cases so much. So the first thing is we got to understand what bitonic is. Bitonic, and were examples in the test, is a shape. A sequence is bitonic if it rises and then declines. So you have monotonically increasing, always increasing numbers followed by always decreasing numbers. So it has that kind of mountain shape. But it is also the case that if you take that sequence and rotate it with the elements going around the other side, the general shape of bitonic is one up peak and then one down peak, because you have to worry about what happens at the margins as you rotate around, right? So as the first element becomes the last element in the generic shape, which is just up and down, then that shifts that minima to the end of the sequence. So let me show you what I mean. So here is a bitonic sequence. It starts at 1 and rises to 6 and declines to 2. But as I shift this around by moving the first element to the last element, you can see that the shape changes. And I can keep doing this until I shift all the way around. So there are going to be 1, 2, 3, 4, 5 shifts to get back to where I was. And the general idea here is I'll use this V to represent a down arrow and the little caret to represent an up arrow. The 6 is the maximal point. It's the largest number in the sequence. And the 1 is the minimal point, which is the smallest element of the sequence. And as I shift this around, you'll see that I still only have one largest and one smallest elements. They're just moving around within the sequence. Okay, follow? So here, it seems that the condition I want to check is that there is exactly one maximum and one minima. So how do I find a maximum and minima? Well, a minima or maxima occurs when the differences, like this number minus this number compared to this number minus this number, have different signs. So I look at 3 consecutive elements, 1, 2, 3, and if it's like that, in other words, it's increasing then decreasing, or decreasing then increasing, then it's either a maxima or a minima. There's a lot of ways I can do this, but notice that it's not necessary to rotate the sequence as long as I'm careful to check around the boundary as if it were rotated. So as long as I scan the list, or tuple, whatever it is, and find that there's exactly one maxima and one minima, including across the boundary, then I can detect a bitonic sequence. Now, I admit this is a little complicated, but the code itself is not that bad. For those of you who grew up with for loops, this should be like you should finally feel good about being able to write a for or a while to solve this problem. So let's see what the overall structure is. First of all, in the specifications on the exam, it says that the sequence must be at least of length 2. Okay? So you need it to have at least 2 elements in the sequence. So I'm just going to check for that outright. If length is less than 2, then I'm just going to return false. It's not bitonic. It can't be bitonic with sequence of less than 2. Then the next idea is I'm basically going to set a counter, and I'm going to step through all of the elements, and I'm going to count how many times I change direction. And every time I change direction, I'm going to increment the counter, and at the end of this loop, if my counter is exactly 2, if that count equal 2, which is a Boolean, if it's true, then that is the case that this is a bitonic sequence. That's what I want to return. If the count is not exactly 2, then it's not a bitonic sequence. It'll return false, which is what I want. So really, the only thing I have left here is to detect change of direction, and I sort of know how to do that already because we talked about how we need to check 3 consecutive elements. We need to consider that window of checking consecutive elements scanned over the entire list as well as across the boundary. So there's a couple of ways you could do this. So the change of direction happens in a sequence, x1, x2, x3, when x2 minus x1 and x3 minus x2. So x2 minus x1 and x3 minus x2 have different signs. So think about it. If x2 is a peak, a maxima, x2 minus x1 will be positive, but x3 minus x2 will be negative. So there's a sign change. And if x2 is a valley, meaning a minima, then x2 minus x1 will be negative, but x3 minus x2 will be positive. So change in sign. Now, remember, L contains unique integers. So this makes our life easy because we don't have to worry about less than or equal to anywhere. Or in fact, we don't have to worry about a difference that's 0. So that relieves that extra corner case. So I have 2 ways of doing this. The one I just described, which is to take the sign check. You take Li minus Li minus 1, so those 2, multiplied by Li plus 1 minus Li, those 2. And if the product is less than 0, then the signs are different because you got a minus and a positive. Multiplied together gives you a minus. Okay, so that's one way of checking. The other way of checking is simply to do explicitly check, is Li greater than Li minus 1, and is Li plus 1 greater than Li? These are 2 Booleans, and they have to be not the same. One of those has to be false, and one of those has to be true. Either way is fine. So here's my completed function. I chose to use the less than thing. And it looks like it's pretty good, but it's important when you do these kinds of things, we have this weird corner case. The corner case is when we wrap around, and it's always best to check that to make sure you got it right. So let's review for a moment what i's values will be. I's values will start at 0 and go right up to the length of L minus 1. So it makes sense, as corner cases go, to check what happens when we're either at one end or the other of that range. So let's see what we got. When I is 0, I'm going to be checking to see if L0 is greater than L minus 1, which is fine, and if L1 is greater than L0, which is fine. So this is the last difference in the list, and this is the first one, and that works. That's good. But when I is length of L minus 1, I'm going to be checking length L minus 1, so length L minus 2, against length L minus 1. So that's the last difference. But then I'll be checking length L minus 1 against length L. And what does this do? What is L of length L? It's out of range, right? You've gone around. The list indices are from 0 to length of L minus 1, and you're trying to access the length of L element. So this range here doesn't work with this configuration. So you really have 2 choices. One is you can modify the range so that your condition works, or much easier, let's modify the condition. So I'm going to refactor my code slightly, and instead of looking at the number ahead of I and the number behind I, I'm going to look, for every I, I'm going to look at the 2 numbers behind it. So when I wrote the condition the first time, I had this integer I, which was an index, and I compared the difference before I with the difference after I. And now what I'm going to do is I'm going to define I to be the last number and compare the difference between the numbers 2 before I and the number right before I. You understand? So instead of, I'm just shifting my comparison over. And you can see that here, that the indices have changed. I have I is greater than I minus 1, and I minus 1 is greater than I minus 2. And when I do that, when I is 0, I'm going to be checking L0 against L minus 1, which is okay. That's the wraparound. And L minus 1 against L minus 2, which is fine too. And when I is length L minus 1, it's length of L minus 3 against the length of L minus 2, and so on and so forth. So I fixed a little error in the wraparound stuff. Now, this has a lot of moving parts, but if you got the iteration roughly right, you're going to get partial credit. And this is my favorite problem. Probably not yours, but it's actually a really interesting problem. And I believe that right before class, right before the exam, didn't we do a lab with a problem like this, where you'd sum a sequence? This is essentially the same problem. So there are two general approaches. One approach is to treat the input integer, n, as a sequence of digits, string digits, and break it apart by casting it to a string and then treating each number individually. Alternatively, you can treat the input as a number and use modular arithmetic to peel off the lowest order digit repeatedly. And each one of these has at least two variants. So we're going to look at 4 solutions. All right? So at least 2 ways, so at least 4 variants, and there's probably more. In fact, there's surely more. I can think of at least 2 more. So let's take a look. So the first thing we're going to do is we're going to try to do this treating the digits as, I believe we're going to do modular arithmetic first. So the idea is if I have a number like 5, 6, 7, 8, I want to peel off the 8, and then I want to add the 8 to having peeled off the 7, and add this 8 and the 7 to peeling off the 6, which gives me 11. Oops, but I have to add those numbers together because they're 2 digits. So you sort of see how the recursion breaks up. So here's my solution. If n is less than 10, it's a 1-digit number. I'm done. Otherwise, I'm going to take n modulo 10, which gives me that last digit, and I'm going to take n integer divided by 10, which gives me the first 3 digits in this case. And what I'm going to do is I'm going to take the digit sum of the first 3 digits. So I'm going to take these 5, 6, 7, and I'm going to compute the digit sum of those. I'm going to add to that the number to that. And then I'm going to take the digit sum of all of that to make sure that I keep getting single-digit numbers. All right? I've got the base case. I have the base case labeled. So we know that everything stops. The recurrence stops when you're down to a single-digit number. And I have the recursive step labeled as well. So here we see one call to recursion, which gives me the single-digit version of the rest of the number, added to the single digit I got from the last part of this number, and then I take the digit sum of that as well to make sure it's decomposed to a single digit as well. All right, so here's the second configuration. It's almost the same. But instead of having 2 recursive calls to digit sum, what I'm going to do is, well, the base case is the same, but the recursive step says take the last digit and add it to the remaining digits. So in other words, take 5, 6, 7, 8, add 8 to 5, 6, 7 to get 575, and then take the digit sum of that, which will recursively break it down. Either approach works. It all depends on how you govern the recursion. They actually do exactly the same number of operations, or they should do the same number of operations. Questions? Let's try the other way around. So let's try the side where we cast integers into individual digits. Now here is where I hinted in the solution you could use a comprehension as long as you were still recursive. I think this is almost the most direct mapping to how I think of the problem. So this is probably the solution I would have come up with if I were asked to do this. Again, the base case is always the same. If it's a single-digit number, you're done. Otherwise, what I'm going to do here is I'm going to take the number, convert it into a string, and take the integer version of the digit in that string, sum all those together, and then recursively call digit sum to make sure that is 1 element long, 1 digit long. It may not be. Now, this may seem a bit of a cheat because I'm doing this sum over all the numbers, but it's still a recursive solution because if the number is long enough, many digits, the sum will exceed one digit. And so you have to recursively call digit sum to make sure that you continue to pack that in until you get back to one digit. Did you guys learn casting out nines as kids to check your arithmetic? Is that really old-fashioned? You guys just use calculators now? Yeah, okay, I thought so. There's a method that they used to teach us in grade school called casting out nines, which is a way of checking complicated arithmetic operations like big multiplications or additions and so on that involved essentially doing this kind of digit sum and throwing out the nines because they didn't change anything. That's what it's called, casting out nines. You can look it up. I almost wrote this as part of the exam, said, remember the method of casting out nines, and then I started thinking, I bet they don't know what that is, so I changed it. But here, this is kind of a direct mapping to me of the idea behind digit sum. Okay? All right, so the other solution that uses the number as string is almost the same, except here what we do is we take the last digit, convert it to integer, and we add the digit sum of the first digits. Oops, sorry, I have a digit sum 4 here because it was my fourth solution, so these should just say digit sum. And you can see that this literally replays that peeling off and repeated addition version with the modular arithmetic. But what's interesting about this one is there's nothing keeps you from doing things exactly. So here, you'll notice that we're peeling off the low order digit and adding it into the rest of it. You could do this the other way around if you want. You could peel off the very first digit and add it to the digit sum of the remaining digits. It doesn't matter which digit you start with. You can start peeling off from the bottom or peeling off from the top. It doesn't matter. If you're doing this with modular arithmetic, the only natural way of doing it is to peel off the lower order digit and work right to left. Here, by changing these indices, you could do things left to right, right to left, doesn't matter. So there's many ways, many variants of these solutions. Okay, now you should be able to see your solutions to the exam later today, as soon as I get a chance to look at them and post them. If you think that your exam was graded incorrectly, there's a mechanism that some of you have already found in Gradescope where you go in, Gradescope, and you say, regrade this problem, and you get to write a little note. If you do that, that is the best way to handle exam regrades. Don't write me about those. Just go into Gradescape and do it there. Okay? Questions? Okay, so before we left for spring break, we were working through the word ladder game, and I'd like to finish this because it's getting really interesting now. So since it's been a week and a few days, I thought I'd review where we were. Remember, we were building a network out of words of 5 letters length. We have this big dictionary of listing of words, 5,757 5-letter words. And we had built a function called makeNetwork that took the list of words. Here it's just 3-letter words, and returned a dictionary with each word as a key and the other words that differ by just one letter as the value. So hat and cat differ by their first letter. Cat differs from hat by its first letter and car by its last letter and so on. Remember this? So we had done this. And we were then trying to find a solution to a puzzle that consisted of a beginning word and an ending word, and asked the question, can you find a path from that word to the other word by a series of steps that changes one letter of the first word at a time? We can do letter changes and get from source to destination. And the key idea here was you start from the source node and you start looking at all the words that are in its neighborhood, words that differ by one character. And then for each one of those, you look at all the words in its neighborhood, words that differ by a second character, and so on and so forth. So it's like dropping a pebble in a lake and watching it spread until you either find that destination word or you exhaust all possible connected paths and don't find the destination word, in which case there is no path. All right, that's the idiom you should keep in mind. So we're going to do this by having two sets of nodes. We have the collection of nodes. We're going to start with a list of nodes or a set of nodes called the explored nodes and the list of nodes called the pending nodes. And the way the search works is we put the source node in the pending list to start with, and then we start this iterative process where every iteration we randomly select one node from the pending list and move it to the explored list while adding all of the neighbors of that word to the pending list. So we're just going to sort of, that's the step that instead of spreading out uniformly, it spreads out one word at a time. So you get this kind of incremental spreading across the lake. Understood? Let's see how it works. So this is the function. It's really not very hard. We have a source, we have a pending set where we have the source, and we have an explored set, which I would like to make a set, but unfortunately, the two empty brackets, curly brackets, is a dictionary, which I don't want. So I have to use the set constructor to make an empty set. And here's my main loop. At this point, all I'm interested in is answering the question, is there a path from the source word to the destination word? Return true if there is and false if there isn't. So what I do here is I first check to see if the destination node I'm looking for is in the pending list. If the destination node is in the pending list, that means it somehow got there. And that means there exists a path. So let's think about it in very simple terms. If the source and destination nodes are the same, then I'll have the source node in the pending list, and the first check for destination and pending will say, yeah, it's there. And that tells me that from any word to the same word, there is always a path. Because as soon as that destination node ends up in the pending set, I return true saying, we got there. Otherwise, I'm going to take an element from the pending set. I'm going to just pick an arbitrary element out of the set. I'm going to use pop to do that because sets aren't ordered. So I'm going to pop out something from pending. That's the item I'm exploring. And I'm going to add that to the explored list. And then I'm going to take every element, every neighbor of item in the network that is not already explored and not already in pending, and I'm going to add that to pending. So this is the step that extends that sort of ripple one more space. And I'm just going to keep doing this until either the destination appears in the pending list or I have no more nodes in the pending list. When pending is empty, I terminate and say false because there was no path. So let's see how this works. So this is a made-up network. We did this on Friday before you left, but some of you may not remember. I'm asking the question, is there a path from node 2 to node 11 in this network? And we look at this and we say, yeah, there's a path right there. There's another one here. There's a lot of paths. This is a very connected network, right? There's a lot of ways to get from one to the other. Some short, some long. There's always a path. But how do I find it? Well, I'm going to start with my pending set with the source node, and my explored node is nothing. And every time through that loop, I'm going to first say, is the destination node in pending? It's not. So I'm going to pop the node off pending. I'm going to take 2, and I'm going to put it in the explored list. And then I'm going to take every node that's adjacent to 2, which is 1, 6, and 3. We can see they have direct links. And I'm going to add them to the pending list. Now I'm going to go around again. I'm going to ask, is the destination node, which is 11, in the pending list? And it's not. So I'm going to pop another node out. This time I got 6. There it goes. And I'm going to add the neighbors of 6, which are 4 and 9, to the pending list. 2 is a neighbor of 6 as well, but I'm not going to add it in because it's already been explored. And remember, my loop checks. If it's not in pending, not in explored, then you add it. So this is sort of a discovery of new nodes emanating out from the source node until I discover the destination node I'm looking for. All right, so let's try again. This destination node is not in pending, so I'm going to pick a pending list node. Here I happen to pick 3. It's all random. So I pick 3, and I put the neighbors of 3, which are 4 and 7, onto the pending list. But 4 was already there, so I just add 7. And you can see that the search now looks like these core explored nodes are sort of the center of this, and all of the nodes that are on the fringe, that are reachable from these core nodes, are on pending. So it's that ripple going across the network. I pop the next node, which happens to be 4, and I add the pending nodes adjacent to 4, which are just 7, but that was already on the pending list, so the pending list doesn't change. Go around the loop again. Is the destination node 11 in pending? It's not, so I'm going to pop a node off that pending list. I choose to pop 9, and I put 9's neighbors, which are 5 and 10, on the pending list. I check is destination 11 in pending? It's not, so now I pop another node out, which is, what did I just pop here? 7. And 7's neighbors, which are 11 and 8, make the pending list. And now as I go around the loop again, I find the destination node is in the pending list, so I'm done. And in fact, there is a path from 2 to 11. I discovered it. Don't know what it is, but I know there's a path. Right? So we've answered a simple question, which is there a path from source to destination? But there's a better question to ask, which is, what is the path from source to destination? And there may be even better questions to ask. Can you find the shortest path from source to destination? Can you find the best path in terms of alphabetical order, for example? Or could you find the longest path, which turns out to be amazingly hard? So there are many variants of this question, but we've answered the very simplest question. The question is, does a path exist? This is a special status of problem in computer science. We've just solved what's called a decision problem. The decision problem always has a yes or no answer. The general form of a decision problem is, does there exist a path from source to destination in a network? It might be, is there a solution to this equation? Not what is the solution, but is there one? So, and so on and so forth. These are all problems that have yes or no questions. And when you get to theory of computation, you'll find out they have special stature and are important in interesting ways. All right, so this was my solution before. But what I would like to do now is instrument it a little bit. I would like to add some additional stuff. I'm going to count how many nodes I actually explore. Gives me a measure of how much work I've done. And I'm going to add some print statements in here using formatted output, you'll notice, like we talked about before. Some print statements in here that give me a little bit of information as I explore. So for example, exploring node item, the length of my pending list is this many elements, the length of my explored list is this many elements. Otherwise, nothing has changed. I've just added a little bit of extra stuff to make it more appealing to the user rather than have it do all this work and type in a question and it says true or it says false. It would be nice to have some more input. And I'm going to add a little driver to this, which you may recognize in part from homework 1. This is a simplified version of what we call the play function. This is going to take a file name, which is defaults to the file with the words in it. It's going to read those words in a variable called w. It's going to create the network with a variable called n. And then it's going to enter a loop to interact with the user. And it's going to ask the user, can you give me a source word? And the source word, so I'll talk about input in a minute. So input will, well, let's talk about it now. Input takes a string, which it prints to the screen, and awaits input from the user. So here I'm going to ask for a source word or Q to quit. So if you're done playing the game, you just type Q. Otherwise, you type the source word, and input will return the string that you typed to source. So the source is now that string. And if source is Q, then I'm done. Otherwise, if source is not in W, meaning that the user typed a word that doesn't exist in my word list, well, it doesn't make sense to start somewhere you don't know about. So we have to have a word in the word list. So when that happens, I'm going to use the continue directive in while. Can anybody remind me what continue does? Do you remember? What does continue do? Go ahead. Actually, good. It says, when you get to a continue, it says, whoa, skip the rest of this iteration and go back and loop again. So what will that in effect do? It'll skip and go back and ask source word. It will be like the annoying little brother you may or may not have that keeps asking the same question. You type the word, didn't find it, just says type the word again. And to get out of that loop, you have to type a word it knows. Little sisters can be annoying too. Not saying. So there you go. So there's my check for a word in W. Otherwise, I'm going to do the same thing for the destination word. And here, I don't want to continue because I don't want to ask for the source word again. So I'm going to put this in a little busy loop, in a little while loop that says if destination not in W, well, destination is initially the empty list, the empty string, and that's not in W. Or source and destination are the same. I'm just going to keep asking for the destination word. And when I finally get a destination word that is in W, I'm going to solve search network, and I'm either going to print out I found the word ladder or no ladder found. Well, so here's the output from my game. I read all the words in. I built a network. It tells me how big the network is. I have a source word. I type a bash. Destination word, a base. It says, found a path, one node explored. These two words are adjacent. So I will immediately explore a bash and find a base in the pending list, and I'll be done. So I'll try another word. Source word, abide. Destination word's a back. Both of these were acceptable. It found a path, abide to a back. I don't know what the path is, obviously, but I can see that I and A changed, and D and C changed, and E and K changed. So it's probably 3 letters long, although it could be more. And it took me 275 nodes. So 275 loops through that main loop that pops the node off pending and puts it in explored. I'm going to try it again. Source word cream, destination word acorn, found the path in 3,400 nodes. And then when I finally type Q, it quits. Questions? It's pretty cool, right? I mean, we've got something that actually does something of consequence. It searches a big network for a path. That's kind of a foundational thing. But it's not a very interesting game, right? If you like word games, yes?
So how long did it take to compute all this?
The largest cost of this whole operation is building the word net. So milliseconds. I mean, this is not a big problem, right? Now, if you played it with Webster's dictionary, now we're talking a little more, right? I'll distribute this code, by the way. As soon as we're done with the full version, I'll post the code so you can download it on the word list and you can play with it. And you should, by the way, go in, edit, change, do whatever it takes so you really understand. My favorite thing to have students do when I hand out a piece of code like this that we've developed together in class is go add print statements. Add extra print statements so you can see how each function is running. For starters, after each function, when you enter the function, print the function name and the argument list so you can see what the calling sequence is. By instrumenting the code that you're given, you can understand how it works, and it's well worth doing. Okay, so deciding that the path exists is a good start, but it's really not very interesting. We really want to know what the path is. And so today, and maybe not finish today, but certainly by Wednesday, we'll finish making the changes that we need to do that. So to know something about the path itself, we're going to need to modify our code. And the reason is, when I move a node from pending to explored and add the explored node's neighbors to pending, I don't keep track of who puts the nodes on pending. That's the critical thing I'm missing. So when I move that node to explored and its neighbors get added to pending, knowing that this node, the node I just moved to explored, is responsible for adding to nodes to pending is what constitutes the path, right? Because it keeps track of how I got to that explored node. So, first of all, define path, shortest, fastest, longest, slowest, the most scenic path. Okay, I was joking here, but it's not a surprise. You have a GPS, or you have Google Maps, certainly. Google Maps is using essentially a version of this algorithm with some sophisticated heuristics. But basically, when you say navigate from my home to school, it's treating every intersection as a node and every street as a connection between nodes. And it is navigating in exactly the way we're doing here to find a path from home to school. The difference is that instead of just finding any path, it's typically trying to find the fastest path or the lowest cost if there are tolls. And so it's that characterization of the path that's what makes GPS navigation interesting, not finding the path. That's easy to do. We just did it. So we built a little GPS system that nobody will want to use because it just finds a path, right? What you really want is like the fastest one. So let's review how this works one more time. Here's my replay of the movie. Isn't this a great movie? I'm not in film studies. I should be, because this could be a nice movie. So we'll notice that when I did this, so the eventual path I find is this one, ends up through 7 to 11. And that path, 2 put 3 on the list, 3 put 7 on the list, 7 put 11 on the list. But I didn't find this path until I'd done a lot of unnecessary exploration down here. Okay? So ultimately, I only know what path I took by reconstructing it back from the destination. And to do that, I need to record, as I said before, which node's exploration is responsible for posting the neighbor node on the pending list. All right, so there are two places we need to record this. When we change the pending and explore structures, which were sets, they're now going to be dictionaries. And we're going to use the dictionaries because that's how I keep track when I move into an explored node. That's how I keep track of who put me there when I explore a node. So the key will be the node, and the value is the node that put me on the pending list. It's my parent. And as I move from pending to explorer, I'm going to keep track of that. So this seems obtuse, but it shouldn't be. It's easier to see. Let's just do the example. I'm going to represent the second argument here. So now these are both dictionaries. The key is the node name, and the second argument is who puts me on the pending list. Well, the original node, 2, the source node, nobody puts me on the pending list. That's the source node. So I'm going to label that with the special symbol none, which says there is no parent. This is, in a sense, the root node, the beginning of our path. Special. But now we're going to do exactly what we did before. I'm going to explore 2, so I move 2 and its value to the explored list. And 2 then adds 1, 6, and 3 to the pending list. But notice that now in pending, the 1, 3, and 6 are the keys, but the values all point back to 2. They tell me, hey, 2 is responsible for me getting explored. 2 was the node that added me to the pending list. Now the next node I pick is, what did I explored? 6, so I move 6, 2 to the explored dictionary, and that adds 4 and 9, which both point back to 6, right there. Right? The next one I explore is 3, so 3, 2 goes onto the explored list, and its neighbors are 7 and 4. 7 gets added with the 3 as its parent, but 4 was already on the pending list. So even though 4 could have been added by 3 or 6, we'd already recorded 4 as being added by 6. So we lose the alternate path. Now this is a critical step, because if I were really interested in finding the shortest path, I would make a choice which one of these two to retain. But because I'm only interested in finding a path, I'm just going to keep the path that got me there first. The second thing you should notice is as I look at the state of this thing, which is all embodied in these two dictionaries, I can sort of, if I were looking for a path from 2 to 9, following the parent arrows back will get me there. From any node, there is a direct path that takes me back to the root node. Any node at all. And finally, you'll notice that I'm always popping a random node from pending. I don't order which node I look at. I just take one at random. In this case, I've just added, what have I added, 6? No, I add 4. And 4 keeps its pointer to 6. And the only nodes adjacent to 4 are 7 and 3 and 6, which were all already on the pending list. So by extension, this yellow arrow is ignored, because 7 had already been placed on the pending list by node 3. And I keep doing this. I add 9. It points back to 6. Its neighbors are 5 and 10. 9 points back to 6 because 6 added 9 to the pending list. And finally, when I pop 7 off the list, 11 gets added here, and I'm done because 11 is in the pending list. But here's the key thing. There is one and only one red path from 11 back to 2, and that's the path I want. So by adding additional data structures, I'm able to retain information about how the algorithm evolved so I can reconstruct the path. And the only thing I have left to do is I need to be able to go backwards and find my path. So I have a new function called findPath. It takes the source and destination node and the state of the explored dictionary, which retained all the relevant red arrows, because when you get to Explorer, those are all the nodes that go backwards. So when I look, I start with a path at destination, starting from the end, And while destination is not equal to source, I'm going to move back one step in my path, and I'm going to append that previous node to the path list. And when I keep doing this, when I get to source, I'm done. I have the list of all of the nodes I traversed in reverse order. So what I'm going to do is reverse that path and return it. Done. So there's my path. I start here, 11. That takes me back to 7. Takes me back to 3, takes me back to 2, and I return the reverse of that list, and I'm done. So this really is not a huge... Notice that we started with a simpler decision problem and solved it. It wasn't very, very interesting, perhaps, but it gave us the skeleton of the solution without all the unnecessary detail of having to keep track of the path as I build it. It let me make progress on the problem incrementally. I had a first solution to the simple problem, and then I incrementally developed it to make it more and more complete. In a sense, this is what I hope that you learn in this class. You've learned all these how to write little functions with clear specifications. The next step is, let's develop these functions incrementally so that we make sure that we're building correct code as we go, rather than trying to solve the whole thing at once and then debugging, because that is not a good idea. It is not effective use of your time. And then the final step in your quest to become a good programmer is, how do I organize the code on the larger scale? In this class, I'm typically going to give you a template. Homework 1 template file tells you what the breakdown is to solve the problem. When you get on into 28, I forget the number of the class, 2820, you're going to talk a lot about that upper level, top level design or architectural process. But in this class, we're going to focus on the lower levels of the process. All right. So remember, the path is the first path I find. Yes, question? Yeah. Okay, so the question about finding a shortest path of a path is a good one. It says, do you need to explore the whole graph so you can ascertain it's the shortest possible path? We have not done that. We cannot say anything about this path. It may be short, it may be long. There's no quality constraint. To get that quality constraint, you might think you have to explore the whole thing, but you actually don't. What you do have to do is you have to keep track of the quality of the path as you build it, which is a little bit more complicated. We will do that this term, but just not on this problem. So this basic algorithm, which has a name, it's called graph search, has many variants. And the one that runs your GPS has that kind of quality control. It doesn't search every possible path on every street in the world to tell you how to walk the 6 blocks to school. It does it in a very directed way, but to do that, there's all sorts of additional structure we need. Okay? All right, so the first path we found, once we find a path, as soon as we have a path, we quit. And then we have to reconstruct that path. There's no guarantee that this is the shortest path, just that it is a path that's legal. So what I'd like to do here is I want to look at that code that we had right here and what we had to do. You'll notice that the first thing we did is we've changed pending and explored to dictionaries now. And that the first element is source and none. And then the only other changes are here when first of all, to check if it's impending, we do the same thing. Otherwise, when we get to a destination impending, I'm going to take that last node and I'm going to make sure that I add it to explore it. Because remember, find path doesn't get the pending list. It just gets the explored list. So I just want to make sure the last hop is in my explored dictionary. So I add that explicitly, and then I quit and return find path. Otherwise, everything else is the same. I'm going to pop an element from item, and I'm going to retain in explored that element along with whoever put me there. Add one like I did before, and then everything else here stays the same. So it's a minor update. Once I decide what I'm keeping track of in that dictionary, it's a minor update to the code I had before. And this is the value of that incremental development. You get the thing working, and then you go back in and you modify it to make it do whatever the next element of stuff you have to do is. All right, so. Okay, so we're going to talk about, I think it was Ben's question, next time about what makes this faster. Yes?
Back on the where you have the program code listed. So after you called out the item where it said, and you added the item question to be explored.
This one here? Or down here? Right here? Yeah.
Why is it?
So because this is a dictionary, and remember, item is a dictionary as well. So I'm adding to explore the key of item with the value of item as a dictionary. This is just, I could have done this with a method to add a pair, key value pair to explored.
Okay, I was just
Yeah, it's just stylistic. It's just stylistic. All right, we'll see you on Wednesday.